a graduate student in the ACS here at Berkeley, and he's interested in learning theory, statistics, and complex computation, and in particular in computational issues with learning theory. And today he's going to talk about oracle inequalities for large-scale model selection.
Okay, so this work's going to be about taking a statistical problem, namely that of model selection, but analyzing it in a framework where the amount of computation available to us is restricted. But at the end, we will present statistical guarantees on the solution in terms of the amount of computation we spent. And the results I present will involve joint work with John Ducci, Peter Bartlett, and Clément Levrard. So let me begin with some with a motivating example for what this model selection problem is and why we might be interested in it. So in well, that's unfortunate. The heading's being clipped off.
You might be able to set it to a higher resolution.
Let's just go on because I think that might take a while. So a common example in many applications that we're interested in is that we want to estimate some parameter that's pretty high dimensional. And in such cases, you don't want to estimate the entire high dimensional model because that doing so takes both that leads to poor performance both statistically and computationally. And what we might want to do is estimate just a sparse model, where so we want to find maybe a vector theta in R to the d, where d is large, that takes non-zero values only on a small subset of 1 to d. And this can be quite challenging because this involves typically a search over all 2 to the d subsets. But in many examples, we have additional structure that's present in the problem. So a particular common situation is that we have some ordering on the complexity of our features that's specified by domain knowledge. For instance, in many natural language tasks, the features we use are based on vocabulary, and so they can consist of individual words or pairs of words or triples of words and so on. And it's quite clear to see that both statistically and computationally, individual words are simpler than pairs, which are simpler than triplets, and so on. In many applications, we want to fit functions to a collection of data points, and we might want to do a polynomial or a Fourier or a wavelet basis fit. And here, the complexity will be determined by the degree of the polynomial or the order of the Fourier expansion that you go up to, and so on. And in computer vision problems, features are often induced by running some sort of filter over the image, and the complexity of the feature depends on the complexity of the filter that is used. And in such scenarios where we have knowledge about the complexity of these features, a natural simplification to use is that I'm going to select a complex feature only after I've selected the simpler one. So I go to word pairs only after I have extracted the maximum statistical benefit I can from individual words. Right? So then feature selection just boils down to selecting the right cardinality of the feature set, right? Because I'm either going to select maybe the first D1 or the first D2 or the first D3 features and so on. It turns out, by the way, that selecting this number in the right way is quite important because for many statistical procedures and computational algorithms, getting this number, the performance critically depends on the dimensionality you use. And so the model selection problem in this case is to find this right number D of the features that we want our model to include. And this and many other examples can actually be encapsulated into a nice abstract framework that we can reason in. So we consider a setting where we have a nested hierarchy of model classes. So I've got a collection of models F1, which is contained in the next collection F2, which is contained in the next collection F3, and so on. So I've got these models that get bigger and bigger, and there can actually be infinitely many of them. For instance, in the example we saw before, Fi would correspond to a vector that takes non-zero values only on the first Di components. So we have this collection of models now. In the diagram, I just show finitely many of them for simplicity. And we've got n data samples that are available to us from which we want to do our statistical inference. Our performance criterion is specified by a risk function that measures the expectation of some loss, some cost measure, and the expectation is under our data distribution. So in particular, given this setup, the goal of the model selection problem is to find a good model I star from this collection of models. And a generic principle is that we want to find this I star to optimize what's called the estimation approximation trade-off. So there are two opposing forces that are in play here. There is the estimation error that asks, given these n data samples, how well can you find the best function in a fixed function class Fi? Right? The function, how well can you find a function that minimizes the risk within the class? And so this typically tends to grow as we go to bigger and bigger models because searching for a good function within that model from a small number of samples becomes harder and harder. The second term, the so-called approximation error term, looks at how well does the best function in the model Fi do compared to the best model overall, so the best model from the most complex class, for instance. Right, and this quite easily we can see becomes smaller and smaller as we go to bigger and bigger models. So these two forces are kind of acting in opposing directions, and we want to find if there is a sweet spot somewhere in this trade-off. So that's the model selection problem. Now the trouble is that both these estimation and approximation errors, by the way, have been defined in terms of the risk function that of course we don't have access to. So typically we define data-dependent estimates of these two quantities in order to solve the problem. And in particular, one common way of thinking about these is, so the first estimation error term, as I mentioned, this becomes worse and worse as we go to bigger and bigger model classes. So this is in some ways measuring the complexity of a model, and so people often replace it or upper bound it with some other estimate of the complexity of the model class Fi that we can either compute in closed form or compute based on data, and we will denote that by gamma I of n based on n data samples for the model class Fi. In the other term, the approximation term, this R of F star part is just a constant offset. We don't really worry about estimating it. What we want to get is this minimum of the risk function, and then we use a general principle again, which is to remove the expected risk with the sample average of our loss function. So we just take the minimum of the sample loss instead of the minimum of the expected loss. Right? And defining the surrogates for estimation and approximation errors this way leads to a very nice and general principle called complexity penalized model selection, where we do two things. First, for each model class Fi, we compute an estimator F hat I that just minimizes the sample average of the loss function. So this gives us functions f hat 1, f hat 2, and so on. Now for each of these, we look at this sample loss that we have already computed, but we also add in the complexity of the model classifier and pick the one that minimizes the sum of these two terms, because these two terms are our proxies for estimation or approximation errors, right? And this, the function from this collection that minimizes is our final estimator f hat n. And plugging in different choices of the complexity term here leads to different model selection methods then. Some common ones being methods like AIC or BIC or the Mallow criterion. And the one particularly important one today for us would be those that are derived based on certain concentration inequalities. Now the reason people are often interested in these procedures is because often we can prove very nice statistical properties about them. So we can prove what are called Oracle inequalities, where we can show that the function f hat n that we select has a small risk. In particular, it is competitive with an Oracle that can actually minimize the sum of the approximation error term and the surrogate for the estimation error through the complexity penalty, and incurs only an additional factor. So here we are taking a minimum, meaning we are actually optimizing over this trade-off, and our estimator only loses an additional term that goes to 0 with the number of data samples and grows only logarithmically with the number of models. So this is very nice statistically because we can handle a large number of model classes, this means, because we are incurring only logarithmic growth here. But let's think about what's going on here computationally. What I do on this previous slide is I compute this estimator f hat I for each model classifier, meaning that my computational performance is going to be at least linear in the number of model classes. And in fact, if you think about it a little carefully, you can actually reason that in many scenarios it's going to be super linear, which means that computationally you actually will not be able to scale to a large number of model classes, even though the procedure can do so statistically. And so it's a very natural question to ask if we can obtain a procedure for model selection that has good properties, good scalability, both statistically and computationally. And that's going to be the question we will try to answer in this work today. And our principle really to try and go towards a solution was to start from a completely opposite viewpoint. So model selection problem, the classical framework starts from a sort of data-centric perspective, and we're instead going to start from a computation-centric perspective and think of a total computational budget, T, of being available to our model selection procedure. Now what this means operationally is I assume that the model class Fi can process an I of t samples in time t. So I can compute my function f hat I on these many samples given time t by some algorithm of my choice. And because I believe that computational problems become harder as I go to bigger and bigger model classes, I assume that these numbers ni of t become smaller as I go to bigger and bigger model classes. So n1 of t is going to be the largest number of samples I can process in time t for the smallest class. Just to give you an idea of what these numbers might look like, for instance, if we think about the feature selection problem that we talked about at the beginning, and we just think of the simple problem of binary classification, then for many algorithms, ni of t ends up looking like t over di up to a proportionality constant. And now even our complexity terms, instead of depending on a fixed number of samples n, for class I they depend on the number of samples ni of t. So we are just going to think of complexity as a function of computation now, which will be induced through NIT samples. So this is our computationally budgeted model selection framework. Now let's think about what kind of statistical guarantees we might want to obtain in such a framework. So we start from kind of asking what's the best possible performance we can hope to have in such a framework. And so we can hope to have an oracle that knows the correct model class, the best possible model class, and devotes the entire computation to it, in which case it will incur a penalty that's the approximation error of the best model class, the complexity penalty of the best model class with computation t, because the entire computation was devoted to that class. And maybe we can tolerate an additional term that now goes to 0 with number of samples ni of t, and we are okay with incurring maybe some logarithmic penalties at most. Right? So getting this sort of a oracle inequality is the kind of gold standard that we would try to compete with, because this is really the best possible. If all the ni of t, if you're in a computationally agnostic scenario with all the ni of t's being equal to n, then this was the best possible we could do. So to just sort of set the tone for our solution, I'm going to start with a simple example of a very, very crude solution that we're not going to use, but gives us some intuition about how we might proceed. And I will actually, for describing this solution, I'll restrict myself to a setup of just finitely many model classes. So I assume I have a total of just k model classes. And a natural first thing to try is to just split the budget uniformly across the classes. So each class has budget t over k. It can process ni at the number of samples corresponding to t over k in that much time. And it just does the same model selection procedure as before, which is to minimize the sample loss, find a function that minimizes sample loss with this many number of samples, and then pick the function that minimizes the sum of the sample loss and the complexity penalty across the collection of f hat i's as before. And with very little work, we can actually prove an oracle inequality about this procedure, but we see there are some losses. Because each class gets a computation only t over k now, you get the complexity depending on the budget t over k, and even here you get ni dependent on the budget t over k, whereas if we look at what we want from the oracle, we want the whole budget t really to appear in here. And for instance, if we plug in the example of the feature selection problem, we see that this actually starts incurring a linear growth with the number of classes now statistically. So that's pretty bad, because we now have a good computational behavior, but our statistical scaling is completely lost. Now the thing that we have to keep in mind though is that this very naive solution does not really exploit any structure in the problem at all. In particular, we have this nice nested hierarchy that induces all kinds of monotonicity properties. So if we define Ri star to be the minimum risk for all functions in class Fi, then because our classes are increasing, Ri star goes down as we go to bigger and bigger model classes. And the complexity penalties go up as we go to bigger and bigger classes. So we have these monotonicity assumptions that we would like to exploit. And the way we exploit them is by doing a slightly different solution that says, I'm not going to evaluate every single model class, but I will actually pick a small subset of them and only evaluate them, and then somehow interpolate to the rest by using this nesting property of my hierarchy. And the particular way we pick this small subset is based on looking at the growth rate of the penalty function, the complexity penalty, with the model class I. So we look at the growth rate of this function. We always include the smallest class f1, and then we keep on going till we hit a point where the complexity has grown by a factor of 1 plus lambda for some lambda, any positive lambda suffices. So when we hit this complexity, we induct the model class corresponding to at least this much complexity, and then we go further up till we hit a complexity 1 plus lambda squared, and there we induct another model class into our collection. And we keep on repeating this process, And the idea is that for many intuitive cases, what happens is initially the complexity grows pretty fast. And so you include classes quite finely. But then the growth often starts to kind of taper off. And there you start including classes very slowly later on. And even here you can see the gap between fj and fj plus 1, for instance, is quite big compared to the gap between f1 and f2. And in particular, so we define some number little s and we include just little s of these models. And we are only going to evaluate those. In particular, it turns out for many examples, it suffices to set the number of models we evaluate to be logarithmic in the total budget. And then we go back and use the same procedure. We allocate the budget T over S to each model class in our collection. And with that much budget, we run the same procedure as before. We find the minimizer of the sample loss, and then we find the minimizer of the complexity penalized loss from this collection of f hat j's. Now the tricky part here is that we have not evaluated every single model, but at the end of the day, we are still going to be interested in a statistical oracle inequality that competes with every single model, not just the ones that we actually evaluated. But the nesting property again comes in critically there, allows us to do this. So we can show an oracle inequality which says that with high probability, we are competitive with an oracle that looks at the minimum of the risk function for class I, and an additional term that depends on the penalty of class I, evaluated with a budget T over S, because that's the budget we allocated, and this additional term that depends on Ni of T over S. And in particular, if we keep in mind that S is typically logarithmic in T, then we see that this is only a log factor worse than the ideal oracle, than the gold standard we had in mind. So just to give you a simple example, going back to the setup of feature selection, what we can show is, in many cases, this just ends up being competing with minimum of Ri star plus an additional factor that up to log factors is di over root t. And the nice thing I like about this result is that, so this is a very clear statistical guarantee, but that's explicitly formulated in terms of the amount of computation we spent on our procedure. Okay, so I'm running short on time here. I should wrap up at this point. I want to say that this is the first computationally budgeted framework that I've seen for model selection problem, and we propose a framework and provide an algorithm that works in it and gives statistical guarantees in the framework. And the nice aspect of the guarantees is that they can be explicitly formulated in terms of the computational cost of the procedure, and they have favorable scalings both statistically and computationally. There are many extensions that can be made to this simple idea that we describe in the paper. So everything I talked about today seemed like we need prior knowledge of the computational budget, but we can be adaptive to it using a simple argument. We can be adaptive to the complexity of the problem. So for instance, if you have low noise in the problem, then you can get much faster rates, for instance, for model selection as we demonstrate. And even though I only talked about nested hierarchies today, you can actually change the algorithm a little bit so that it can work for both nested and non-nested model collections. And this requires using sort of online algorithms, using ideas from Karen Bandit's algorithms. So yeah, that's all I have to say. Thanks a lot for your attention.
Yes, Alekh again.
Namely that of model selection, but analyzing it in a framework where the amount of computation available to us is restricted, but at the end we will present statistical guarantees on the solution in terms of the amount of computation we spent. And the results I present will involve joint work with John Ducci, Peter Bartlett, and Clément Levrard. So let me begin with some with a motivating example for what this model selection problem is and why we might be interested in it. So in well, that's unfortunate. The heading's being clipped off.
You might be able to set it to a higher resolution.
Let's just go on because I think that might take a while.
He's a graduating student in the UCS here at Berkeley, and he's interested in learning theory, statistics, and complex computation, and in particular in computational issues with learning theory. And today he's going to talk about oracle inequalities for large-scale model selection.
Situation is that we have some ordering on the complexity of our features that's specified by domain knowledge. For instance, in many natural language tasks, the features we use are based on vocabulary, and so they can consist of individual words or pairs of words or triples of words and so on. And it's quite clear to see that both statistically and computationally, individual words are simpler than pairs, which are simpler than triplets and so on. In many applications, we want to fit functions to a collection of data points, and we might want to do a polynomial or a Fourier or a wavelet basis fit. And here, the complexity will be determined by the degree of the polynomial or the order of the Fourier expansion that you go up to, and so on. And in computer vision problems, features are often induced by running some sort of filter over the image, and the complexity of the feature depends on the complexity of the filter that is used. So a common example in many applications that we're interested in is that we want to estimate some parameter that's pretty high dimensional. And in such cases, you don't want to estimate the entire high dimensional model, because that doing so takes both, that leads to poor performance both statistically and computationally. And what we might want to do is estimate just a sparse model, where so we want to find maybe a vector theta in R to the d, where d is large, that takes non-zero values only on a small subset of 1 to d. And this can be quite challenging, because this involves typically a search over all 2 to the d subsets. But in many examples, we have additional structure that's present in the problem. So a particular common Okay, so this work's going to be about taking a statistical problem